Having defined the support vector machines optimization problem, now we want to solve it. So what does this mean? We want to find the vector W and the bias parameter B. So here is our optimization problem, right? As we said before, we want to find this W and B such that the length of W is small and also the sum of the slack penalties is small, and the slack penalty parameter C is trading off between the length of the margin and the misclassifications we are making. So our goal is to find B and W, basically solve the above optimization problem. A standard way how to do this would be to say use a solver. A solver is nothing else than a mathematical package or a piece of mathematical software where we are writing down the structure of our optimization problem, and the software is able to solve it for us. If we would look at our optimization problem, the optimization problem requires a quadratic solver. Why quadratic solver? Because here W is multiplied with itself, which means this is a quadratic objective function. So we would have to have a software that solves quadratic optimization problems, and this software is called quadratic solver. The problem, of course, is that these solvers are generally slow because they are meant to be built for general quadratic problems, while given that this is a support vector machine, we can use the structure of the problem to come up with a much better solution. So the idea is that solvers that are kind of off-the-shelf software are very inefficient for large-scale data, and we have to build a custom solution that will optimize our SVM optimization problem. So the question is, how do we do that? So our goal is to estimate W and B. And the way we will do this is we will come up with an alternative approach. Imagine that we want to minimize this function f of B and W. Okay? So there is some abstract function that has two parameters, and we want to find the value of these two parameters, B and W, such that the function is minimized. What is the function? The function is very simple. This is simply the 1/2 sum over all the coordinates over all the dimensions of the squares of the values of W. So this is the first part, the margin maximization part of our optimization problem. And then we have the second part, which is this empirical loss part, where we say plus the slack penalty C times the sum over all our training examples, right, 1 to n, and then the value of the slack penalty, which is 0 if we classify correctly, or 1 minus our distance from the boundary. So this is the optimization problem, right? So we want to find W and B that minimize our function f. So what we notice now is that this is a very, very nice function, and one way to optimize nice, smooth functions is to compute their gradient, right? So one way to optimize convex functions, and our function in fact is convex, is to use what is called gradient descent, which basically means is that given a function now of some abstract parameters z, right? In our case, z is W, B. What the idea is the following: if I have z and on the y-axis I plot f of z, all that we will want to do is we will want to start at some point. We will want to compute the derivative or the gradient of that function at a given data point, and then we will want to make a small step in the direction of the gradient. That will give us to the new value. We will reevaluate the value of the gradient there, and again make a small step in the direction reverse to the gradient. And if we keep iterating this, eventually we will minimize the function and get into the value of the function. So we will use this same idea and this same intuition to optimize our SVM optimization problem and the function f. So our goal, as we said, is to minimize function f. So what we want to do is first we will want to compute the gradient or the derivative of our function f. And the way we will describe the derivative is with this kind of upside down triangle, right? So our idea is that we want to compute the gradient with respect to wj, and we will label the gradient as this kind of triangle, and then which coordinate or which dimension do we want to compute the gradient with respect to. So the idea is gradient of coordinate j is simply our f of b taken gradient with respect to variable wj. If we compute the gradient, all other w's are just constants and their derivatives are 0. So the only thing that survives is wj, because we have wj squared. Derivative of that is 2wj. Then conveniently we have this 1/2 here, which cancels the 2, and all that is left is wj. And then if we also take we also have to take the gradient of the empirical loss. So what we are saying here is this is the slack penalty times the sum over all the data points, the gradient of the empirical loss evaluated for wj. So how do we compute the derivative of the empirical gradient? So if our classification is correct, if which means we correctly classified the training example, then the value of the derivative is 0. And if we misclassified, then this is simply the jth coordinate of training example I times the value or the class of that training example. So what this now means is that we were able to compute very simply using basically high school math what is the gradient of our objective function for a given dimension or coordinate j. So now that we have the gradient, we want to use our what is called the gradient descent method, which is a very simple method. We will start at some location x, and all we are doing then is to say, let's evaluate the gradient for a given dimension. So we will iterate over all the dimensions. We will evaluate the gradient at that given dimension by simply going through all the data, compute the sums introduced on the previous slide, and then we are updating that coordinate of our vector w in the direction that is reverse to the gradient. One thing that we have to keep in mind is that we have this parameter eta, which is what is called the learning rate parameter, which basically tells us how big step are we going to make. Basically, when we compute the gradient, how much are we going to move in the direction that is the opposite of the gradient. One thing to note that in this case, and this is a big problem, is that computing the gradients takes linear time, right? So computing the gradient takes linear time. Why is that? Because here we have to go over all the data, all the training data to compute the value of the gradient. So this means if we want to to do, let's say, 100 steps of the gradient descent, we have to scan over our training data 100 times, which means that this method will be super slow when we have large amounts of data. And the question is, can we do this faster? Can we kind of still do gradient descent while not needing to traverse over the whole data set to do one step of the gradient descent? So our next question will be, how do we speed up this method? And in order to speed this method, we will use what is called stochastic gradient descent, right? So before we were just talking about gradient descent, or what is also known as batch gradient descent. Now we will use the idea of stochastic gradient descent. And the idea here will be that kind of instead of evaluating the gradient over all the examples in our data set, we will simply evaluate the gradient at each individual example. So the idea is that the gradient for coordinate or dimension j and training example I is simply the wj plus c times the gradient for that given training example I. So how this changes our optimization problem is that now we have two for loops, where the first loop goes over all the data, second one goes over all the coordinates, and we simply say, let's evaluate the gradient at coordinate j for a given data point, and then let's move in the direction of the gradient at that individual data point. So what does this mean is that our calculation of gradient is now very fast, right? We just are evaluating gradient at a single data point, and we are making a step. But because this takes very little time, we'll be able to make many small steps. And the method that does this is called stochastic gradient. What's the difference between stochastic gradient descent and gradient descent? The difference is in a sense that gradient descent computes the exact version of the gradient, kind of what is the direction in which we move towards the valley. Stochastic gradient descent, we can think of it as a noisy version of gradient descent, right? So one potential idea would be, imagine that we want to minimize this three-dimensional function where I have the dimensions x and y, and the dimension z is kind of inside the slide, and I want to converge here to the bottom of this valley. If I were to use gradient descent at every step, I would move closer along this red line. However, if I would be using stochastic gradient descent, sometimes my gradient will be very noisy because I'm evaluating it using just one training data point. So I may my optimization might kind of dance around, but eventually I hope I will reach the minimum. So while using gradient descent, we are kind of guaranteed that at every step, as we are making more and more iterations, the value of the objective function, in our case this would be WB, is steadily decreasing. Using stochastic gradient descent, the whole thing is much noisier. However, the benefit of stochastic gradient descent is that computing it is much easier, so we will be able to do many more steps than what gradient descent is able to do in the same time period. So now let me give you a quick example of how stochastic gradient descent support vector machine works in practice. And this is an example from real life, where the idea is that we want to use what is known as Reuters Corpus Volume 1. So this is a set of articles from Reuters, where every article is categorized into a different topic. So the idea is, what we want to do is we want to predict a category of every newswire article, right? Whether it talks about sport, politics, international news, and so on. So in this data set, we have more than 700,000 training examples or documents. And what we will do is we will represent every of these 800,000 training examples with a 50,000 dimensional vector, which basically means that we will have one feature or one dimension per word. We will remove words that are very common. We will also remove words that are very rare, and we will keep the rest of the words. We want to use these 700,000 documents to figure out what is a good value of W and B, and then we will want to evaluate our predictions on a small test set of 23,000 documents. So there are three interesting questions that we may want to ask. First, the question is, does stochastic gradient descent really minimize our objective function, right? So how successful is stochastic gradient descent as a method for finding the minimum of our objective function f of WB? Second thing is, how long, right? How much processor time, how much wall clock time does it take for the stochastic gradient to find the minimum of the function? And then, of course, the question is, after we find this W, how well does this value of W generalize to the future data, right? What is the error on the training data set? So to answer the first question, how successful and how long does it take stochastic gradient descent to find the minimum value of f? So standard support vector machine would, for example, take 23,000 seconds. A fast version of support vector machine would take 66 seconds. While, for example, the version of support vector machine that we introduced, the stochastic gradient descent based SVM, would take 1.4 seconds to find W and B that minimize f. So that's the answer to the second question. How long does it take? Answer to the first question is, what is the value of the objective function, right? How good of a solution do we find? And for example, what you find that the values of the solutions are pretty much the same. So all of the three different variants of support vector machines are able to find the same value of the objective functions. They were all equally successful in minimizing the function f. And then what is the error on the training set? In all these cases, the error is about the same. So what do we conclude on this? We conclude that support vector machine using stochastic gradient descent took only 1.4 seconds, so it was like more than 10 times faster than any other method, while at the end achieving the same performance.